Good morning, students. So in last video I had covered peak reading AC voltmeter circuits, okay, where we had seen a series voltmeter, okay, series capacitor peak meter and the digital, okay. So okay, just a minute. Okay, so this was my digital peak voltmeter. Okay, so as I said in the last video, conventional instruments of this type are available with very less error, less than 2% error. Okay, so today we'll see the next type of peak voltmeters, that is peak voltmeter with potential dividers. Okay, so here, right, see, this is the figure. Okay, so this is a peak voltmeter with a capacitor potential divider. As you can see here, this part forms the potential divider circuit. Okay, now CS, what you see here, okay, see this capacitor CS, okay, so this capacitor CS is charged to a voltage, this CS is charged to a voltage proportional to the peak value which is to be measured. Okay, and the voltage across C2 is made use, right, voltage across C2 is made use of in charging the storage capacitor CS. Okay, so what you next is talking about RD. You can see here RD. So RD is a discharge resistor employed to permit variation of Vm. Okay, whenever V2, okay, variation of Vm across CS whenever V2 is reduced proportional to the peak value of the measured voltage. Okay, peak value to be measured, right. Now the indicating meter is either an electrostatic voltmeter, ESV, what we had seen, or a high impedance vacuum tube voltmeter. So this discharge time constant CS into RD is designed, right, discharge time constant of see here, this CS into RD is designed to be about 1 to 10 seconds. Okay, so this gives rise to a discharge error which depends on the frequency of the supply voltage what we are giving through this. Okay, now to compensate for this charging, okay, to compensate for this charging and discharging errors because of this resistances R2 and RD, okay, R2 and RD, now the circuit is modified, what you can see here, okay, it's a modified circuit, okay, where you can see a measuring branch, an equalizing branch, we have the storage capacitor CS, we have capacitance C2, we have R, and we have one more capacitor C1 with a micro ammeter. Okay, so the measurement of average peak is done by the micro ammeter. Okay, so above this, see, this circuit was designed by Hafele. Okay, so above this one more modification to compensate for charging errors was given by Rabius. Okay, this circuit was given by Rabius. So these two circuits along with this circuit can be considered for explaining the peak reading AC voltmeter with potential dividers. As you can see here, C1, C2, R2 form the potential divider circuit, and here I have, see, this part forming as a capacitance divider, and here also I have capacitance in a potential divider. Okay, so this is how A peak voltmeter with potential dividers is used for measuring the peak voltages. Okay. So next we'll go for the spear gap measurement. Okay, if I go back to the main slide where I had given you a table of various techniques. See, this is the measurement techniques. Okay, so you can see here okay, so you can see here the right. So we use spear gap measurement to measure DC voltages. Okay, we can use the spear gap and spark gap to measure AC voltages. We use it for measuring the impulse voltages also. Okay, so today we'll see the spear gaps for measurement of DC voltages, AC voltages and high frequency AC voltages and impulse voltages. So, spear gap measurement. A uniform field spark gap will always have a spark over voltage within a known tolerance under constant atmospheric conditions. Okay, so this I had shown you when I was explaining what is meant by spear gap or a spark gap. Okay, so therefore a spark gap can be used for the measurement of the peak value of the voltages. Okay, if the gap distance is known, right? Now this you will understand when we go through the laboratories. Okay, HV labs, when we do, you'll understand this. Now a spark over voltage of 30 kilovolt peak at 1 centimeter spacing in air at 20 degree centigrade and 760 torr. Okay, this has to be torr. Okay, pressure occurs for a spear gap. Okay, for a spear gap measurement or any uniform field gap. Okay, but experiments have shown, okay, that these measurements are reliable only for certain gap configurations. Okay, there is a limit of gap configuration. We cannot exceed the gap length more than the pre-specified value. Okay, above it gives you a wrong measurement. So normally one spear gap, only the spear gaps are used for voltage measurements. Okay, so in certain cases, uniform field gaps and rod gaps are also used, but accuracy of rod gaps is less, okay, as compared to my spear gaps, right? So next, the spark gap breakdown, especially the spear gap. Okay, see, spark gap can be a spear gap or a rod gap or uniform gap, non-uniform gap. Okay, but here we are talking about the spear gap. Okay, see, here I have mentioned only spear gaps are used for voltage measurements. So the spark gap breakdown, especially the spear gap breakdown, is independent of the voltage waveform and hence is highly suitable for all types of waveforms, right, from DC to impulse voltages of short rise times which would be greater than 0.5 microseconds. Okay, so as such, spear gap measurement can be used for radio frequency AC voltage peak measurements also, which would be having the frequency up to 1 megahertz, right? So here I'll show you the assembly. Okay, spear gaps. There are two assembly. Okay, spear gaps can be arranged either vertically like this or horizontally like this. Okay, so vertically is this with lower spear gap. Here lower spear gap is connected to ground. Okay, or horizontal spear gap, okay, with both spears connected to the source voltage. See, either I can connect both the spears to source voltage or I can connect one spear to high voltage okay, high voltage source, and other sphere I'll bring it and connect it to ground. Okay. Now under horizontal, so generally we go for horizontal arrangement. Okay. Now you can see here, one is the insulator. Okay, okay, so see, one is the insulator. Okay, two, what I have said is the sphere shank. Okay, this one edge. Okay, sphere shank. 3 is the operating gear. Okay, 3 is the operating gear. Here I have 4 is HV connection. Right, you can see at the top here it's the HV connection. All here it is. Okay, now P is the sparking point. Okay, this is the point where the sparking occurs. D is the diameter of the sphere. S is the spacing between the sphere. Okay, A is height of sparking gap above ground. See, this was a sparking gap. So A is height of sparking gap above earth. Next, B. Okay, B is the radius of clearance from external structures. It means this much has to be the radius of clearance. X. Okay, X is the high voltage lead, should not pass through this plane, right, within a distance of B from P. Okay, now same is this here. Okay, you can see here also. Just a minute. Okay, so you can see here also 4 is the HV terminal which is given, 3 is the operating, 2 is the operating shank, sphere shank. Okay, 3 is my operating gear. Okay, 4 I said you HV connection. See, P is the sparking point. X, high voltage lead should not be passing through this plane. B is radius of clearance. S is distance. D is diameter of the sphere. Okay, so you can same. Okay, whatever is I have mentioned it here. Okay, these all holds good for horizontal or vertical arrangement of the gaps. Okay, now here, right, what we do is the voltage to be measured is applied between the two spheres. Right, here the voltage which I have to measure. Okay, so voltage which is to be measured is applied between the two spheres. Okay, here and here, it's applied here with a spacing of S between them. Okay, so it measures the spark over voltage. Okay, this measures the spark over voltage. Okay, now generally a series resistance is connected between the source and the sphere gap. Okay, now see, if this is the source, if this I have connected it to voltage source, here one resistance I'll have. Okay, I'll be having one resistance. So work of this resistance is, first thing is to limit the breakdown current, right, and second is to suppress the unwanted oscillations in the source voltage. Okay, if the breakdown of this gap occurs. Okay, now the value of the series resistance which we will be incorporating can vary from 100 to 1000 kilo ohms. Okay, for AC to DC voltages, and if you want to measure impulse voltage, it would go up to 500 ohms. Okay, now see, this is what I said. Okay, there is a series resistance usually connected between the source, right. The work of the series resistance is to limit the breakdown current and to suppress unwanted oscillations. Okay, and the value of resistance can go from 100 to 1000 kilo ohms or to 500 ohms. Okay, now in case of impulse voltages, to obtain say 50% flashover voltage, two voltage limits differing by not more than 2% are set, such that on application of lower limit value either 2 or 4 flashovers take place, and on application of upper limit value 8 or 6 flashovers take place. Okay, when you want to measure the impulse voltages, we do this type of testing. Okay, then what we do, we take average. Okay, we take mean of these two limits is taken as 50% flashover voltage. Okay, so in any case a preliminary spark over voltage measurement is to be made before actual measurements are done. Okay, so what I mean is here, right, for AC and DC voltage measurements, it's a simple technique. Here between the two spheres, okay, we apply the voltage which is to be measured. As soon as flashover occurs, that is the breakdown voltage we say. Okay, but in case of impulse voltage, what we have to do is, okay, two voltage, okay, there has to be two voltage, right, 10 to 20 kilovolts or 10 to 15 kilovolts. So at 10 kilovolts, okay, see, it is said here not differing more than 2%. Okay, voltage difference should not be more than 2%. So if I consider an example, say 10 kilovolts to 12 kilovolts I have to measure. So what we do, at 10 kilovolt I apply a voltage of 10 kilovolt and check for 2 to 4 flashovers. Okay, and then I apply 12 kilovolts and I check for 8 to 6 flashovers. Okay, then I take the mean of these two limits and is taken as 50% flashover voltage. Okay, so in any case a preliminary spark over measurement, so initially you have to measure the spark over voltage, okay, before actual measurements are done, right. So this is in the case of measurement of impulse voltages. Okay, now we'll go for cap construction and assembly. So construction and assembly I have already shown you, right. You can draw the figure, right, and label all the parts neatly. Now here some basic configurations are given. Sphere gaps are made with two metal spheres of identical diameters d with their shanks, operating gear and insulator supports. Okay. Now sphere gap measurement are generally made up of copper, brass or aluminium. Okay. So generally we go for the latter one because the latter is having the low cost, right. Now the standard diameters of the sphere are 2, 5, right, as per my BIS standards, going up till 200 centimeters, right. The spacing is so designed and chosen such that the flashovers occur near the sparking potential P. The spheres are carefully designed and fabricated so that their surfaces are smooth and the curvature is uniform. Okay, the radius of curvature is measured with a spirometer at various points over an area enclosed by a circle of 0.3d. Around the sparking point should not differ more than plus or minus 2% or the nominal value. Okay. Now the surface of sphere should be free from dust, grease or any other coating, right. The surface should be maintained clean but need not be polished every time, right. But if excessive pitting occurs, pitting means if the surface is no longer smooth due to repeated flashovers or sparkovers, they should be smoothened. Okay, they have to be smoothened, right. So the dimensions of the shanks used, the grading ring used, okay, whatever with the respective spheres, what should be the ground clearance, everything you can see from these figures. Okay, from these figures you can see what should be the distance maintained or what should be the dimensions. Okay, now we are talking about the sphere gap measurement. We saw how do we go for measurement. We have seen what is the construction, right, how the sphere gaps are assembled, right. Now we'll see what are the factors influencing the spark over voltage of sphere gaps. Okay, so here various factors that affect the spark over voltage of a sphere gap, right? This we had already done in module 1, right? But still we'll brush it up, right? First thing is the nearby earthed objects, right, will have an effect on the spark over voltage. Second, the atmospheric conditions and the humidity. Okay, we know what is a good conductor. So moisture content in the air will obviously affect the spark over voltage. Next is irradiation, right? And last one is polarity and rise time of the voltage waveforms. Okay, polarity means if I am applying DC voltage, positive and negative polarity will have the effects on the spark over voltage. Okay, so we'll see one by one. First one, effect of nearby earthed objects, right? The effect of nearby earthed objects, right, was investigated by Kuffel by enclosing the earthed sphere inside an earthed cylinder. It was observed that the spark over voltage is reduced, okay, and the reduction was observed to be delta V is equal to m log of B by D plus C, where delta V would be the percentage reduction, B is the diameter of earthed enclosing cylinder, D is the diameter of spheres, and S is spacing. M and C would be my constants. Okay. Now whatever reductions was measured by Kuffel was less than 2%. Okay, less than 2%. So it is if the specifications regarding the clearances are closely observed. Okay, here I have shown you the figure, okay, and I have given you the clearances. Okay, if you see here, I told you B. Okay, you can see here in both the figures I have mentioned B. Okay, now what is that B? B was radius of clearance from external surfaces. Hence, if the specifications regarding the clearances are closely observed, okay, the error is within the tolerances and accuracies are specified. Okay, so the nearby earthed objects would have a considerable effect on the spark over voltage. Okay, so next one, atmospheric conditions and humidity. Okay, atmospheric conditions and humidity. As I said, the spark over voltages of the spark gap depends on the air density, which varies with the changes in both temperature and pressure. So if the spark over voltage V under test conditions, T is the temperature and P is pressure in torr. If the spark over voltage is V0, okay, then under STP, okay, standard conditions of temperature or standard temperature and pressure, temperature being 20 degrees centigrade and pressure being 760 torr, V is given as K into V0, okay, where K is a function of air density factor D, which is given as D is equal to P divided by 760 into 293 divided by 273 plus T. Okay, now the relationship between D and K, see, all these equations are derived by earlier done experiments. Okay, we need not derive the formulas here. Okay, so you have to remember V is equal to K into V0 and D is the correction factor, right? How do we apply correction factor, right? Depending on the relationship of K and D. So this is a predefined table, right? If D is equal to 0.70, see here when we are calculating D, because we know what is the current pressure and what is the current temperature, you have to calculate D. Whatever D value you get, that value of K you have to apply it in this equation. Okay, so this is the table giving you the relationship between correction factor K and the air density factor D. Okay, the humidity, okay, the humidity effect increases with the size of spheres and is maximum for uniform field gaps. Okay, this you have to remember. Okay, next, the spark over voltage increases with the partial pressure of water vapor in air, and for a given humidity condition the change in spark over voltage increases with the gap length. Right, next we will see effect of irradiation. Right, see, this was the effect of humidity, okay, or effect of atmospheric conditions where air density factor and humidity are affecting the spark over voltage. Next we'll see effect of irradiation. So illumination of sphere gaps with ultraviolet rays or X-rays aids easy ionization in gaps. It means here in this figure I said to check the spark over voltage, what we do, we give this a voltage, okay, and we wait for breakdown of this air gap to occur. Okay, but in case of irradiation, what we do, we can use we can use UV rays or ultraviolet rays or X-rays, so that initially we can trigger the sphere gap, okay, the air gap which is there between the two spheres. Okay, so what it will do, it will 20 to 30% it will almost ionize the gas, the air which is present between the spheres. Okay, and the rest of the work will be done by the voltage which we are supplying. Okay, so illumination of the sphere gap with ultraviolet or X-rays aids easy ionization in the gaps. See, easy ionization in the gaps. The effect of irradiation is pronounced for small gap spacings. Okay, so this is good for small gap spacings. A reduction of about 20% in the spark over voltage was observed for spacings of 0.1 times of D to 0.3 times of D for a 1.3 centimeter sphere gap with DC voltages. Okay, with DC voltages. Now irradiation is necessary for smaller sphere gaps of gap spacings which are less than 1 centimeter. Okay, so this irradiation is not used to initially ionize the gap if the gap spacing is large or the sphere diameter is more. Okay, it is only done for smaller sphere gaps and smaller gap lengths. Okay, next we will see effect of polarity and waveform. Now, experimental investigation showed that for sphere gaps of 6.25 to 25 centimeter diameter, the difference between positive and negative DC voltages is not more than 1%. Okay, I said you polarity, right, has an effect, but this effect of polarity was not seen for more than 1%. However, for smaller sphere gaps which are less than 2 centimeters, the distance was about 8% between the negative and the positive impulses of 1/50 microsecond wave. Similarly, the wavefront and wavetail time duration also influence the breakdown voltage. Okay, I hope you remember wavefront and wavetail. Okay, I showed you, we have seen the graph of impulse voltage. So this was the graph. This was wavefront, this was wavefront, and this is wavetail. Okay, so wavefront and wavetail will also have the effect on the breakdown voltage. For wavefronts of less than 0.5 microsecond, okay, see, impulse wave has the wavefront time of 1 microsecond. Okay, but if the wavefronts are less than 0.5 microseconds and wavetails are less than 5 microseconds, the breakdown voltages are not consistent, and hence the use of sphere gap is not recommended for voltage measurements in such cases. Okay, in such cases when your wavefronts and wavetails are not 1/50 microseconds, such voltages are not recommended and such measurements are not recommended for these cases. Okay, I hope up till here it was clear, right? So next video we'll go ahead with potential dividers for impulse voltage measurements. Okay, what we have done till now is the potential dividers for AC voltage measurements. Right now we will see the potential dividers for impulse voltage measurements. Okay, so this will continue in the next video. Thank you.